Hi, welcome to Physical Science 1.4 on gas laws. You're going to need your formula sheet for this today. Let's start with Boyle's law. In your notes, please write, Boyle's law shows the relationship between pressure, how tight a gas is packed, and volume, how much space an object takes up. It is an inverse or indirect relationship, meaning as the pressure increases, the volume decreases, and vice versa. On your formula sheet, the formula for Boyle's law, and please write Boyle's law inverse, is P1V1 equals P2V2. That means that the pressure times the volume before has to equal the pressure times the volume after. Pressure is measured in three sets of units, kPa, atm, and mmHg. We'll talk more about that. Volume is measured in centimeters cubed and liters. Now, centimeters cubed is generally for solids and gases. Liters is for gases and liquids. To solve a Boyle's law problem, you simply multiply together because you're going to be given three of the four numbers, 2 before and 1 after, or 2 after and 1 before, and you multiply the two together that you have and divide by the third number to get your answer. Here's a pattern that might be helpful to fill in. It's simply a series of boxes, pressure volume before equals pressure volume after, kind of like we did for momentum. Let's look at an example. Hydrogen is stored at 1.3 atm in a 3-liter container. If it were to be released into a 50-liter container, remember gases expand to fill the container they're in, what would the pressure be? Well, P1V1 equals P2V2. You would have 1.3 times 3 is equal to something times 50. Multiply together and divide, you should get a pressure of 0.078 atm. Notice that the units do have to match. You can't switch units in the middle of the problem. Okay, so this is another teacher's video that I found that demonstrates some of these gas laws. I don't have the ability to do those in our classroom, so I found a video to help you. This is a Boyle's law demonstration.
Giant marshmallows are great fun at campfires, but have you ever wondered how they're made? It's an application of Boyle's law. They take regular-sized marshmallows and they make them larger. Marshmallows have air in them, right? So all you have to do is you have to decrease the amount of pressure on the air inside the marshmallow, and the volume should increase. Let's try it out. I'm going to take a whole bunch of normal, everyday, common marshmallows. Hopefully we can see those on the camera. I take a whole bunch of them. You know what? We'll put the big one in there just for fun. Okay. We'll see if we can zoom in. Turn on the bell jar. There we go. I think we can see those just fine. Turn on we'll put the bell jar on. Remember, do not try this at home. This is for science. And we're going to turn on the bell jar, turn on the vacuum pump, close the valve, and watch as these marshmallows grow to campfire roaster size. They're getting bigger and bigger and bigger. Most definitely bigger. All right, now that
So Boyle's law is pressure times volume. Okay, so as the pressure decreased because he was sucking the air out, the volume increased because Boyle's law is an inverse relationship. Charles' law shows the relationship between volume and temperature. It is a direct relationship, meaning as one goes up, the other goes up. As volume increases, temperature increases. So on your formula sheet, Charles' law is a direct relationship. V1 over T1 equals V2 over T2. Again, we're looking at before equaling after. Volume over the temperature before is equal to volume over the temperature after. And this is a direct proportion. Volume is measured again in liters and centimeters cubed. Temperature, however, has to be measured in Kelvin. So if you're given the Celsius temperature, simply add 273 to get the Kelvin. To solve the proportion, you simply multiply diagonal. You'll either have 2 diagonal in this direction or 2 diagonal in this direction and divide by that third number. Again, this little pattern of volume over temperature may be helpful. So here's an example of Charles' law. Balloons at 300 Kelvin have a volume of 2.5 liters. If the temperature is increased to 500 Kelvin, what volume would they occupy? Well, your equation is V1 over T1 equals V2 over T2. You would start by making sure you have everything lined up together. Your first number you're given is the first temperature, 300 Kelvin. At that volume of 2.5 liters, so those two go together. And then if the temperature increased to 500 Kelvin, that goes on the bottom, what would the volume be? Multiply diagonal and divide, and you should get a volume of 4.17 liters. This one coming up is a demonstration of Charles' law.
The question is, how do I take a hard-boiled egg and get it in here? The answer is not as hard as you think it is. The gas law involved here, you could argue that it's Charles' law, and you could argue that it's Guy Lussac's law. Either way that you argue it, you're dealing with a similar situation. In order to get the egg into the bottle, which, by the way, the egg does not fit. I did take the shell off the egg, but otherwise it's just a regular old hard-boiled egg. My methodology is this. Fire. Okay. The fire goes in here. It eats up, well, it removes, well, watch that. All right. What the fire does, there are a couple possible explanations. One of the things that the fire does is it uses up a lot of the oxygen, turns it into carbon dioxide gas. If we go by that way, the number of moles has changed here, which means that the pressure is going to go down inside this flask. Other people like to claim, and I kind of like it this way, that the temperature of the gas inside is really, really hot. When I put that egg on there, it puts the fire out and it starts to cool down. That means that the pressure inside is going to decrease, which means that the pressure on the outside pushes the egg in. Now the real question is, how in the world do you get an egg out of a bottle? So how to get the egg out of the bottle? Increase the volume in the flask, and you're going to increase the amount of pressure inside. And there we go.
Remember that Charles' law is volume over temperature. It's a direct relationship. So what we expect to happen with the ivory soap is as the volume increases, as the temperature increases, the volume will increase.
Let's find out, shall we? Set the microwave for a minute. Oh, by the way, don't try this at home. You'll ruin your own microwave. You can see on the right side of the soap right now what's going on. Oh. Ah.
Finally, we have the combined gas law. It puts Boyle's law and Charles' law together. It shows the relationship between pressure, volume, and temperature. It's both direct and inverse. And that's the equation. P1V1 over T1 equals P2V2 over T2. And again, we're looking at the before and the after. So, pressure is measured in ATM, mmHg, and kPa. Volume is measured in liters and centimeters cubed. And temperature has to be measured in Kelvin, and you have to convert to Kelvin if you're given Celsius. To solve this, you're going to multiply diagonal, which seems a little weird because you're going to have 5 out of the 6 numbers: pressure, volume, temperature, and volume, let's say. So you're going to multiply diagonal. So multiply, 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 and then divide by the other 2 numbers. Divide, divide. Okay? Here's an example. A child has a toy balloon with a volume of 1.8 liters. The temperature of the balloon when it was filled was 20 degrees Celsius, and the pressure was 1 atm. If the child were to let go of the balloon and it rose 3 kilometers into the sky, where the pressure was 0.667 atm and the temperature was negative 10 degrees Celsius, what would the new volume be? So, again, all temperatures need to be converted to Kelvin, right? And all ones need to stay together. So 20 degrees Celsius is 293 Kelvin. Negative 10 is 263. When you set up the work, be sure that everything stays together. So your first volume is 1.8, your first temperature is 293, and your first pressure is 1. Then, afterwards, after the release, the new pressure is 0.667, the new temperature is 263, and we do not know the new volume. So you're going to solve like a regular proportion and take 1 times 1.8 times 263, multiply diagonal, then divide by 293 and 0.667, and you should get an answer of 2.4 liters. Now, also on your formula sheet, there are some standard values that you need to know, because some questions say, what would that be at the standard temperature? Well, your standard pressures are 1 atm, 101.3 kPa, and 760 mmHg. Your standard temperatures are 0 degrees Celsius or 273 Kelvin. Well, those are demonstrations of Boyle's and Charles' law. Hope they help. Thanks for watching.